Data, what do we do with the data?
Analyze it.
Okay, so we're going to analyze it. Let's get a little more, let's break that down into a little more specific chunks. What specifically are we going to do to analyze that data? What are we going to look for? How are we going to go about it?
We need to organize it at least.
Okay, so we organize it. When we say organize it, can you give me some specifics? What kinds of things do we do?
Graphs or charts.
So we graph it, or chart it. Are there other ways that you've seen to organize data?
Fitting different equations to it.
Excellent. And let's actually make that its own over here. So once we have that graph or chart, we can see some kind of patterning in the data. So the reason we organize is to see patterns. And once we see those patterns, we can, and for us this will be mostly what we do, we will actually fit some kind of curve, a curve that matches that pattern. Find an equation that matches the data as closely as we can get. Captures patterns as much as we can in that data. Once we have that, what do we do with it?
Like test it?
Okay. So we test it. What does testing it really consist of? What would we actually do?
Did it make predictions according to that equation that you made, and then compare those to actual experimental results?
Very good. Anything else we use it for? Well, actually, we've got it up here already. We make predictions using it, which is sort of the whole point. Mathematics, when we use it in applications, is very much like a telescope or a microscope. We use it to try and see things that you can't see with the naked eye. So we have this situation, this experiment that we've done. It gives us some data. Anybody can look at the data. But what we're interested in are some hidden things inside of that data. It's trying to extract patterns from the data that you don't necessarily see by just sitting there and staring at the numbers. And then using those patterns to figure out things that we don't know or can't see just by doing the experiment. All right. Questions about the process? This one down here, fitting the curve, means that you need to know shapes. So that when you see a certain shape in a graph, you say, oh, that's this kind of a function. Or this shape is this kind of a function. Or things like that. So, just as a sort of quiz here, and I apologize for those of you who have to crane your necks now to see all of this. But let's run through some common patterns. So if you had a data set that looked like that.
Linear.
Okay. So this is a line. Linear. You have a data set that looks like that.
Parabola.
Okay, so we could probably put a parabola on that one. Maybe quadratic.
Also be a sine.
Could possibly be sinusoidal. How would you differentiate between those if you were in a real life situation where you got data like that?
Didn't the case study we looked at anything say like it could have been parabolic or exponential, but because we knew how the bacteria was growing in the we look at the situation that we're testing.
Yeah, so we take something we know, we go back to the actual situation, the biology, the geology, the physics, whatever it is, and try and apply our sort of our meta-knowledge to the situation to figure it out. What's the key difference between a quadratic function and a sinusoidal function? If you had to give me one key difference between them. Sure.
Sinusoidal is periodic.
Yeah, this one's periodic. And this one, not. So, if I look at the biology, the physics, the chemistry, whatever it is I'm dealing with, and I say, does this repeat over time or not? If it repeats over time, sinusoidal would be the better choice. If it doesn't repeat over time, quadratic's the better choice. All right, so let's suppose we had something that looked like that.
Logarithmic.
Okay, so log.
Irrational.
Okay. Or rational. Anything else that can look that way? Exponential. Any others? Actually, could be a square root. Square roots have that sort of Nike swoosh look to them. This one just be flipped over. Alright, so we have a lot of them. If we try and differentiate between them, we're interested in their mathematical properties versus their physical properties. What kinds of distinctive features does a log have that, say, an exponential doesn't? I'm going to force you to go back to college algebra and remember everything you know about graphs.
Brother Cut.
Yes.
The exponential can go beyond the y-axis, couldn't it? While the log couldn't,
And why can't the log?
because that's bad.
Yes, it is bad, and the bad, if we put a really specific name on bad, somebody said it, has a vertical asymptote. And so, whereas an exponential has no vertical asymptote, however, an exponential has what? Has a horizontal asymptote, which we will abbreviate to A.
I know with logs, like, no light and sound on
Mhm.
a logarithmic scale. Why is that?
Completely arbitrary. It was a choice of man.
And people
Logs-
are like, oh, just put everything on a logarithmic scale and it'll work.
Right.
And I still don't know why.
The reason is that when you look at, say, an earthquake, for instance, and you look at the total amount of energy, you want to measure how big the earthquake is. Well, a natural way is to look at how much energy was released by the earthquake. That's what sort of determines it. And so, but when you look at how much energy an earthquake releases, it's unbelievable. It's massive amounts of energy. And they also vary on huge scales. So the smallest ones we can measure really release really quite little energy. On the other hand, the one that caused the tsunami in Japan releases unbelievable amounts of energy. And so if we were to actually report how much energy the earthquake released, the numbers that we would be using are unintelligible to man. They're like the national debt. $14 trillion, I have no concept of 14 trillion. I don't even know what that means. If you printed that much money, you would have to cut down every tree in the world. And so, no, I have no idea what 14 trillion means. And so what they do instead, the reason they're using logs with both decibels and with the Richter scale is that what a log does is it takes really large numbers and makes them very small. So if you take here you're always talking about log base 10. So if you take log base 10 of a billion, you get out 9. So if your earthquake emits 1 billion joules, and this is, I'm playing a little fast and loose with how they do it. It's all relative to a certain base intensity. And so if you have something that's 1 billion times stronger than that base intensity, then your Richter scale reading is a 9. If it's 1 million times stronger, then your Richter scale would be a 6. If it's 1,000 times, it would be a 3. If it's 100 times, it would be a 2. And so it allows them to take these values, which if you looked at the actual value you're interested in, the actual energy would be all over the board, huge discrepancies between the numbers, and would be getting into numbers that I don't really know what you're talking about, and it compresses them down into numbers that we can talk about. Same thing with decibels. Which means that if you went, you wouldn't know Jethro Tull. Maybe you would, I don't know, probably not. Anyway, he was a rock star back when I was a kid. And my electronics teacher went to his concert. Of course, he was a nerd, and carried his sound meter with him. And Jethro Tull, the concert, would get up to levels, the same level that you would get if you're standing behind a jet engine, which causes hearing loss and things like that. And so he had his earplugs, but so he would go and make those kinds of measurements. But a Jethro Tull concert is, it's like 10 to the 130th. So you're 130 times, no, 10 to the 130th times as big as, say, listening to a stream flow. Yeah. So it's just to take those kinds of unbelievable numbers and put them into something we can play with. All right, good question. We'll need to...
Yeah, can you